So let me remind you where we were last time. And actually, maybe I should start by apologizing that this lecture is probably going to be the most technical lecture of the whole mini course. I tried to keep all the technical details out, but it's still, I have to talk about at least some technical machinery. But, you know, no pain, no gain. So we have to do something to get where we want to go. OK, so let me remind you where we were. So we introduced the symbol classes, and which I had a lot of indices and whatnot. So let me write down this version. So this is what I wrote down. So A in here, and then I had like lots of RNs, which I'm going to skip often. So this just meant that A was C infinity on Rn cross Rn cross Rn. And that some seminorms of A were finite. So I wrote it down the other way, but I did write down the seminorms eventually. So OK, let me write it down the estimate way first. So we had dz alpha, dz prime beta, d zeta gamma of A was less than some constant. And then I had orders of growth in every variable. So let's say L1. And then what the delta did is I allowed myself, so it's going to be a times. I will allow myself to lose delta derivatives whenever I differentiate in any of the variables. And here delta was to be between 0 and a half. And in fact, remember, delta was really small, so it's epsilon. And really the only example of relevance for non-zero delta was if you take this angle bracket zeta to the power m. So I also allowed, I'm going to make a comment about this. I also allowed m to depend on the variables. So if I took this, then it's something like its z derivative. This was just dzj of m times log zeta. I mean log zeta times zeta to this m. And so what this estimate is saying here is that when you differentiate in z, you shouldn't be gaining in zeta, so that's fine. But you shouldn't be losing either, and here you're losing a log zeta. So this is so any delta positive makes this OK. Because that was really the only point of delta. Okay, and I'm going to really ignore this delta non-zero, but I do want, at the end of the day, I do want to be able to work with these sort of things. And so the other thing I want to remind you of is that this was equivalent to a sort of compactified version of looking at things, which was we had this Rn bar. This was the radial compactification. Of Rn, so as a ball, with sort of 1 over r being the boundary defining function, so defining infinity in Rn, in other words. And then we had this Vb of Rn. So these are vector fields tangent to smooth vector fields tangent to the boundary of the compactification. And then such a statement. So let me just not write down the all index version. So let me say A is in, for example, at 0. Sorry about this. Rn. This is exactly equivalent to saying that if you apply any vector fields in here to A, this remains bounded. So here V1. And m was arbitrary. I mean, k was arbitrary. Okay, and then the other, we also had, I said a word about classes of symbols with expansions, and that corresponded to C infinity of the compactification. So, sorry, And the expansion things, I call them, I think, classical, so CL. So these are things with expansions, and they corresponded to A and C infinity, R and bar. And the expansion was just the Taylor series at the boundary. Okay, so that's where we were. Oh, and so one more thing I did, I also told you how to get from these two operators. So we had this map I, which I'm going to abuse notation and call a bunch of things the same. So I'm going to call, I think I called something slightly different I last time. So we also made sense of, well, maybe I'm going to write it like this. So this was a bilinear map. And so what it was is just so in principle, this only makes sense when the order of A, so A here is in SM. It only makes sense if m is less than the negative of the dimension because of the problem with the zeta integral, but we did an integration by parts to show that actually it makes sense, period. And so I also call this AU at Z. So it defines an operator A from, so here U was a Schwartz function, from Schwartz functions to continuous functions with a polynomial bound given by this L1. But so not what I didn't say, but let me say it now. So last time we showed that A mapped S to something like Z to the L1 times L infinity Rn. It was actually continuous, so intersection C0 Rn. So what I would like to say is that, in fact, so very similar arguments give, so similar arguments show that A does map Schwartz functions to Schwartz functions. All you have to notice is, so for, I mean, what does this mean? I.e., if you take Z to the alpha, dz to the beta of this IA U Z, this is still going to be, for example, you can equivalently say this is bounded by Z to the some constant times Z to the L1, the constant depending on alpha and beta. Okay, and so this you can see very easily because what happens if you differentiate in this Z variable? Well, you get some, well, it either hits this or it hits this. If it hits this, nothing happens. If it hits this, you get down a zeta. So it's bad because it gives you more growth. But anyway, things were possibly quite bad in the beginning. So all this means you have to do more integration by parts, and you are OK. And then if you multiply by z, then again, that seems a bit bad. But you just write zj as zj minus z prime j plus z prime j. The z prime j is harmless because it's a Schwartz function. So just it doesn't do any, I mean, it changes the seminorm of you have to use to get this bounded, but so what? And then this z minus z prime j is good because just notice that the zeta derivative of e to the I z minus z prime dot zeta is exactly, so this is a 1 over I in it, is exactly zj minus z prime j times e to the I z minus z prime dot zeta. So when you have something like this in front of the exponential, you can just replace it by a d zeta j and then integrate by parts, and everything actually gets bare. So the upshot is that, in fact, these operators we defined are really map Schwartz functions to Schwartz functions, doing it and do so continuously. And it's actually even bare because really the map I, in fact, I, so this is going SM, L1, L2, whatever orders we had, cross Schwartz functions. So this is supposed to be some Schwartz function, some scripty looking S to Schwartz function. So it is not going to be very visible. So this map, all right. So this map is continuous. So I mean, in a lot of places, so as long as you're doing purely algebraic things, you might not worry too much about continuity. But when you So for example, when you can construct inverses or almost inverses, then you don't have to worry too much about continuity properties. But for a lot of purposes, it's really quite important. So you don't want to forget about this completely. OK, so now we have, so this says that corresponding to the symbols, we have associated operators. And then the obvious question to ask is, are these operators closed on their operator, the set of operators we get? So I should give it a name. So I'm going to call, by a slight abuse of notation for the moment, I'm going to call psi ml of Rn to be just the range of I. So I'm just going to call I of, I'm going to call I of. So I'm going to think of I as now the map from two operators. So the range of I on these symbols, and right now I'm just going to say very haphazardly where L is L1 plus L2. OK. Right now these are just numbers. OK. So I mean, of course, I should make a statement that this is actually independent. So let me just make the statement, in fact. The range of I. So that's actually easy to see directly, but also follows from what we're going to do. The range of I only depends on L1 plus L2. OK. So this is our, and then I also had the symbols where the sub-infinity symbols where you didn't get this extra gain in z and z prime, so not present for what I call Sm sub-infinity. And so correspondingly, we can let psi m sub-infinity Rn just to be the image of ISM. OK. So now we have operators on Schwartz functions. So you can ask, how do operators' theoretic properties behave? And so I mean, for example, are these closed under composition? And so the main theorem is that this psi, well, I guess the way I should say this collection psi ml of Rm, which I'm not going to write down. So here ml in R, this form, I don't know, I think I should quote something like a bifiltered star algebra. But rather than saying what the bifiltered star algebra is, I'm just going to say what this means. I mean, there's just i.e., I'm not going to formally define this, i.e., what we have is that if you have two operators, first of all, the adjoints, that's easier. So if A is in psi ml, then you can take its adjoint relative to the standard Euclidean, the Lebesgue measure, the L2 inner product. So A in psi ml implies that A star is in psi ml. And if A is in psi ml and B is in psi m prime L prime, this implies that AB is in psi m plus m prime L plus L prime. And so the analog is that the sub-infinity is the same. So for example, A in psi m infinity, B in psi m infinity implies that AB m prime is in psi m plus m prime sub-infinity. So let me send this up. So in fact, we get more detailed information about this in just a moment, but let's keep this as is for now. The way to, I mean, there are many ways of proving it, but the way I want to do, the way I want to get at this at least very briefly, since this is some of the, this and sort of how it's proved there, or what else is proved when you prove it, are the sort of the main technical, some of the main technical things. So for that purpose, I actually want to have a lemma, which is the following. So this lemma is going to say that we made this definition of psi where we associate operators to these functions of, this is like three sets of variables. And this lemma says that this was too generous. I mean, we didn't really need all these three sets of variables. So the lemma says that let me put it this way. So if A is in if A is in SML1 2, then there exists a unique AL in S. So I had three sets of variables, but I already talked about what happens if you drop one of them, so that's fine. There's a unique AL in SML, where L is just L1 plus L2, such that I of A is equal to, let me write this way, I of pi L star AL. I mean, what I mean by this notation is that I have these variables, z prime, zeta. I have this map pi L, but L is for left, where I keep the left variable and just pull back AL, which is just a function of z and zeta, to regard it as a function of z prime and zeta, which is independent of z prime. Take the corresponding oscillator integral and the operator, and that's the same as I of A. So this says it was really unnecessary to have this third set of variables. So this, and in fact, it's way better than just this. You can really compute these modulo irrelevant things. And in fact, A has an asymptotic, AL has an asymptotic expansion, which is, well, I don't know. Should I get my constants right? So it's going to be it's going to be a sum over multi-indices alpha, and it's going to be something like I to the alpha over alpha factorial dz alpha d zeta alpha A. So zz zeta z prime here. So first differentiate in the z prime variables and then evaluate at the diagonal. Okay, so and so here this is an asymptotic sum. Now what does this correspond to? So notice that what happens here for SM L1 L2. So when we have this, what happens? The terms, the alpha term is in. So what is it in? So it's going to be just a function of z and zeta. And what's going to happen, its order is going to be m minus alpha in the zeta variable, because we differentiate it alpha times. And then because you're evaluating the diagonal, the two weights, the z and z prime, are the same. So you just get L1 plus L2. And then again, because the differentiations also give decay in z, I also give decay, we also get an alpha here. And then on the other hand, for this other class I had, then the analogous statement is Sm minus alpha, period. So there's no gain, no decay gained. I mean, even if I add, I can't remember whether I allowed or not having a growth in z or z prime. I could have allowed that. So no decay gained in z prime, or in the z variable. Okay, so that's the basic lemma that goes into proving this theorem. And so given this lemma, I could have just started with this taking symbols of depending on two sets of variables, just defining psi DOs like this. So this is, by the way, this is the definition of just the left. This is called the left quantization. And it's again left because this is sort of the left variable, the z. And of course, I should say that there also exists similarly. There's a unique AR such that so if pi r is the right projection, IA is I of pi r star AR. So this is by definition the right quantization. Again, it similarly has a formula, and the only difference is that AR has assuming I got my sign there right, it has a minus sign. So if I didn't get it right, then it doesn't have a minus sign. I think I got it right. Well, and I have this dz. OK, so just to be less confusing, I'm going to write z prime zeta. OK. So I mean, this would be called something like a left reduction. So you can get rid of the dependence on the right variable, and this would be called something like a right reduction, that you can get dependence and get rid of dependence on the left variable. OK, so given this, why did I make this more general definition? And now I have to work to prove this. If I just started with this as the definition, then I wouldn't have to do any work to prove this lemma. So it's in fact really useful to have this more general perspective. So one is, by the way, what I'm going to talk about this, is that if you really look at that integral up there and ignore the z prime integral, or instead if you want to think distributionally, add the z integral as well, and pair with Schwartz functions in zz prime, that's the prime example of a conormal distribution as defined by Hermander associated to the diagonal. So that exponential, the exponent in the exponential is really just a phase function parametrizing, linear phase function parametrizing the conormal bundle of the diagonal. So, so it's very natural in that way to have the zz prime zeta dependence. But more importantly, since you're not talking about that, it's actually really useful to have this. So let me now show you, given this lemma, why is the theorem true? So given lemma, and so this is going to be, I think, the only real technical thing I mean, I'm not going to do this fully, but I want to indicate this. So how does the theorem follow? Well, actually, for the first part, you don't even need the A star part. You don't even need the lemma. So not needed for first part. So how do you show that if A is upside O, then A star is upside O? Well, you just have to write out what AU inner product some phi is. This is the L2 inner product. And so you have to, you again have to keep remembering that this is defined as an oscillator integral. So you, for example, at first do everything for sufficient negative orders and then use a density argument. So this is just right, so this is just the integral, and now we have an L2 inner product as well. So get yet another integral, e to the I z minus z prime dot zeta a z prime zeta, and I applied it to some u. But now I also integrate it against a phi, but I have a complex conjugate here because of the inner product. And I integrate now in every variable like this. So I can rewrite this as by doing, so here phi is supposed to be also some Schwartz function, and just as u. And so I can now rewrite this by doing the z prime integral last. So leave out the z prime integral, and then what I have is, the z prime integral I'm going to leave out. And so what I have is dz d zeta, and then I have a uz prime dz prime. And then now what I want to do is to put the whole complex conjugate over it. So it's the same as, OK, let me put the u in front. And so what I have is a complex conjugate. And then I just have to reverse the order of the variables. Zeta phi z, I have to put a bar over it. I think that's it. Right? And so now notice that this is nothing but I of something like, let me put it slightly informally, the complex conjugate of A like this. So this is to say, I might put it like this. So this is the order of the variables here is wrong. We are thinking of doing the integral. The original function is in the z variable, so the z prime is sort of the variable on which the result depends. So the role of the variables is switched. So this is the z prime reversed. Okay, so this applied to phi, something like that. The whole thing complex conjugated. So this says that the adjoint, the L2 adjoint of a pseudodifferential operator is a pseudodifferential operator, and it's actually just given by the oscillator integral correspond to the complex conjugate of A with these two base variables reversed. Okay, so that for that we didn't even need the theorem. For the composition, we do need this. So what we do is we write A as the left quantization of something. So because the lemma, we can do it. Write B as the right quantization of something. Again, because of the lemma, we can do it. And then AB applied to some U. So this gets a bit messy somewhere notationally, but anyway. So this is just going to be the integral of, okay, there's maybe a 2 pi somewhere, e to the I z minus z, let's call it, I don't know, double prime or something, dot zeta. They have an A z double, sorry, I got rid of the z double prime. There is a left quantization. That was great. Like this. And then what I have here, because there's no z double prime dependence on what I have here, I just have the Fourier transform of BU. Okay, but on the other hand, BU I wrote as the right quantization of something. So that means this B has no dependence on the output variable. So the last integral, the zeta integral, is just producing an inverse Fourier transform. So you can write this as further I'm sorry, I didn't have the z double prime here. Sorry, I got rid of this. Right, that's the Fourier transform here. Sorry about that. Right, so it would be a minus z double prime dot zeta, but that's exactly what this Fourier transform is doing here. And so this is really the Fourier transform of the inverse Fourier transform of, and of course we're going to cancel this, and then now we have another integral, and then it's going to be minus I z prime dot zeta prime b z prime zeta u z prime d z prime, so that, and the whole thing d zeta. Okay, so all I did was I plugged in this bu where the little b was independent of the left variable because you wrote as a right quantization, and because of that, the oscillator integral can just be written as the zeta part can just be written as an inverse Fourier transform. So now I just cancel these two things and then just observe. So very badly in terms of board use, I'm just going to put it here. This is just 2 pi to the minus n times the integral of I z minus z prime dot zeta. And all I have to do now is I have to multiply these two things together. Okay, and so if I call this thing here C, depends on everything. So this is the product of two symbols. You easily check that this is a symbol, and so this is going to be in S. So if A was in, of those classes, this would be a symbol in S m plus m prime. Actually, whatever it works out to, I think it's probably L prime or something like that. So anyway, that's what you're going to get out of this. And so this is exactly a pseudodifferential operator with our definition. So, and not only that, since you get this product, you can really say that this AB is the left quantization of something, again, by the lemma. So maybe I erase the very beginning, but not the expansion, and then get back to that. So in fact, this also gives AB is the left quantization of some new thing. So I had a C there, so let's call it a CL, whatever the CL is. And then you can compute this. And the easiest part to say is that if I write CL, so CL can be computed asymptotically in this sense. Asymptotically. If I write as A as the left, so say you decide that I love left quantizations. If you write A as this, so I called this actually A before, but let's call it AR now just for clarity. B as the left quantization of some BL. Okay, well, when you rewrite B as the right quantization, all you have to do, you have to use this formula. Notice that all terms except the zeroth term, when alpha is equal to 0, are actually in a bare space. So in this case, in both orders, in this case, just in the differentiability orders. So notice that so then B equals QR of some BR, where BL is equal to BR mod the gain here. So say Sm minus 1 in the first case. L minus 1. So if the B is equal to BR modulo that, and then AB is equal to QL CL, where again, we just took the product of these two things. So what I get is AL Z zeta times BL Z prime zeta, restricted at, but now you want to rewrite as the left quantization of something, so I have to just restrict to the diagonal, and then do this, first do the differentiations. As soon as I differentiate, you get something that's more decaying, so you are going to ignore it when you write modulo. So the upshot is that CL is just equal to AL BL mod, again, one lower order. Okay, so this is the, and of course you could do a full, sort of a full expansion. So that's the basic use of this lemma and having the dependence on both variables. So by the way, for the adjoint, what I would get is just A bar if I write to do this the same way for A bar. Okay. Questions about this? Okay, so let me just say a word about how you prove this lemma. So it's not going to be anything amazing. It's actually very easy. But to prove the lemma, all you have to do is to use, in fact, what I wrote down earlier and erase. So let me just make a remark. To prove lemma, okay, so to prove the lemma morally, all you have to do, and then you have to work to prove it not just morally. Go for it. I'm sure it's not. Oh, yes, sorry. Thank you. It's not. It's a very good question. I don't know why I was writing the wrong thing. So. Right. Did I? No, there it was right. Okay, good. So to prove the lemma, what you want to do is, right, so we had this, this I is defined by, so let me just write it informally. This is just this oscillatory integral. I'm just going to write it informally like this. Really apply it to something, blah, blah. And so what I really want to do is I want to get rid of the z prime dependence. So what you do is just expand A in a finite Taylor series. So that is, of course, with the remainder, so with the integral remainder. So of course, this is the thing that one should always use, Taylor series with integral remainder. So expand infinite Taylor series in z prime around z. And so what you have is that A is equal to a finite sum, and then whatever the Taylor series is, alpha factorial z prime minus z to the alpha, and then you get the d z prime to the alpha of a, and then I get to evaluate that z zeta, and I get the remainder term plus Rn, which depends on everything. So it's not so good in this sense. But of course, you have an explicit formula for this, and the integral formula shows that this is in fact in a Baire space. This is because of, I mean, what does it involve? It involves the integral formula involves the alpha derivative. So it's the nth derivative, the next term. So it's this s m minus n, whatever, whichever one. I did it in z prime maybe. So maybe L2 minus n, whatever it is, something like that. So this is this is a much Baire space. Okay. So this is a much Baire space. These don't depend on z prime except having this explicit factor here. And then now you just say that z prime minus z to the alpha times the exponential is equal to d zeta, maybe it's minus d zeta to the alpha of the exponential. So that's what I wrote down before without alpha, just the j's. And now integrate by parts. Yes? Because I mean, what it is really the alpha, the nth derivative. Yeah. So, I mean, it's even without the integration by parts Baire, right? Because what this is like an integral of sort of the sum alpha equals n, and then it's something like n over alpha factorial 1 minus t. Oh, sorry, there's a z minus z prime to the alpha. Maybe this is minus 1, whatever it is, and then you have a d z prime. You're right. That's right. You're right. So let me write it down. I should have, yeah, it's after this. It's going to be there. You should have kept it like this, alpha, and then I have an a, and then this is evaluated at some intermediate point, dt. Right. So it's not quite there yet. What I should have done is keep it like this. Plus some, say, alpha equals to n, and then r. I'm going to call it Rn comma alpha. This is not yet better in zeta, but it has these beautiful, so let me put here a z minus z prime to the alpha. It's not yet better, but it has the z minus z prime to the alpha. And now you integrate by parts, and now it's Baire. Yes, exactly by this. Okay, but so you can see where these d zetas come from here. They really come from this Taylor series, z prime minus z to the alpha, and then that becomes minus d zeta to the alpha, and when you integrate by parts, it's d zeta to the alpha. So that's what's really producing the terms in the expansion. Okay. So we actually proved at least one lemma. And, well, the theorem proves from the lemma. Well, no, it didn't prove the lemma. We morally proved the lemma. So what we really proved, right, is that the lemma said that there is something that's completely independent of the z prime variable. What we proved, right, so the quantization of this, I of this, is in, you just get, well, not right, so I of this whole thing is going to be in Sm minus n, because and then L1 plus L2 minus n. So it's better in both the z and the zeta sense, but in both the differential order and the decay order sense. But it's not 0, right? So now, if you so first of all, anything you want to ever prove, you can do it this way. But of course, it's not perfect. So if you're a perfectionist, then you cannot possibly stop here. Even though for any purpose this would be sufficient, if you're a perfectionist, then you want to use an asymptotic summation argument to like a Borel summation to really sum the full series here, and then it's not hard to show once you've done that that you can really the remainder term that you still get a remainder term, but it's going to be order minus infinity, that you can just write it also as something in the range of QL. Okay, so that would be the full proof of the lemma. So 3/4 of the proof is what I have not written down, but that's all sort of a bit beside the point. So I've done the part that's important. All right, so we have the main result, which is that psi DOs are closed under composition. You can compute products. In fact, let me just say one more thing. If you just go one order farther in the computation, what you get, so you can write this product, by the way, in Bayer forms too, but I'm not going to write it, the full expansion in the Bayer form too, but I'm not going to do it. Or maybe before saying what I was going to say, let me now make a definition. So and so this definition is where the difference again between this between the regular and this sub-infinity classes shows up. So the definition is that the principal symbol in so this psi ml is so for A. If you write an operator as the left quantization of a symbol A, is just the class is the equivalence class of A in SML mod SM minus 1 L minus 1. So versus in psi m infinity, where we just get the equivalence class of A in Sm sub infinity mod Sm minus 1 sub infinity. Okay. And so so put it this way. So if I write, my notation will be that that this is the principal symbol sigma ml of A. And here my notation is going to be that sigma sub infinity comma m of A. And then with this notation, what we have is that the principal symbol of a product is the product of the principal symbols. And then similarly, okay. The thing I should point out is that this is a function space. Well, it's a quotient of function spaces, and so as far as multiplication is concerned, this is a commutative algebra. I mean, again, there's some quotient here, so I have to say a few more words really. But so what we are doing, what this map sigma does, is it starts with this operator algebra, which is non-commutative, and then maps it into a commutative algebra in which it's much easier to do calculations. So the whole point of this is exactly this property that it maps some non-commutative sort of quantum object into something that's commutative, so somewhat classical. So maybe I can say it somewhere here. So for an algebraist, what would capture, what would say, what this does is that sort of algebraically, what we have is we have a map. So of course, psi, let me write it down for this. This is sitting inside. So this is just the inclusion map in psi ml. So this is inclusion. And then now we have this principal symbol map into this commutative algebra. Well, so put them together and whatnot. So, and then algebraically, what you'd like to say that this, in fact, is a short exact sequence. So, I mean, certainly the principal symbol of something here is going to be 0 by the, it's going to be 0 just by the definition. If something has 0 principal symbol, then explicitly from how it was defined, it comes from here, etc. So this is somehow what says the principal symbol captures pseudodifferential operators modulo low-order operators. That's what this really says. And in the setting of the of the other algebra, the sub-infinity algebra, the same thing holds, except that lower order is only in the differentiability sense. Okay, so let me just do the, let me keep this and say what this means for commutators, since they're going to be important. Oops, sorry. And so this is what relates to the Lie algebra properties for vector fields I mentioned before. So if you have two pseudios, prime, and then you take the commutator, so by the definition of product, and that this form an algebra, sort of filtered algebra, whatever, is going to be here. But what is its principal symbol? Of order, of this order m plus m prime, l plus l prime, equals to, well, it's just ab minus ba, which is 0. This is exactly the commutativity statement of multiplication of functions, i.e. of numbers. So this is just 0. And so what this says is that, in fact, this commutator is a pseudo of lower order. OK, so once you know it's a pseudo of lower order, you can ask, what on earth is its principal symbol as a pseudo of this order? In fact, and so for that, you'd want to actually just use this expansion, which I'm not going to be writing down. But if you just use the expansion to one order further, you get that this is given by 1 over I times the Poisson bracket of the principal symbols. Right, so the Poisson bracket is just, you know, A comma B is just some d zeta j A d zj b minus d zj A d zeta j b. And so this is the Poisson bracket. And so this is exactly the sort of the quantum classical correspondence that this is the thing. The Poisson bracket is in sort of symplectic geometries in terms of which classical dynamics is described, while quantum mechanics is about operators. And so from an evolution point of view, it would be described in terms of commutators. So this is exactly the correspondence between them. OK, so maybe I can jump ahead of myself, since now I have this formula, and say one more thing that will be useful later on. And then I don't have to feel so bad about being behind, because in some aspect I'm ahead. So a third related aspect of this is you can do one more, well, you can do many more things, but you can do one thing that's very easy to do and is very useful to do, which is to include a semi-classical parameter. So this is a semi-classical analysis. So this is from tomorrow, so I don't have to do it tomorrow. And so what here happens is that we add an extra parameter, h, and so it's supposed to be small, so say in, I don't know, 0, 1 or something. And then you care about what happens as h goes to 0. So h goes to 0 being of interest. I mean, for any finite value of h, nothing is happening. We are just in standard pseudo setting. And so, so here, what we are doing is we define a quantization, or is also the integral in an h-dependent manner. So here we define I of a comma u to be, so with the scaling, the right way to do it is to put the h here. and then into the over H. And then we could also allow this to depend on H. Here, relatively little matters, maybe a smooth dependence on H down to H equals 0. I mean, including at H equals 0. But instead, bounds would work just as well. Because the important thing is H is acting so H is acting as a parameter. So there's no differentiation in H. So it doesn't really matter precisely what we do in H. And so, so this is maybe I should add the sub H. So for H positive, this is up to a reparametrization exactly of the integral we had before. So nothing changed. So as before, but of course not uniformly, not a priori uniformly, as H goes to 0. So what happens as H goes to 0? So rather than doing the full thing, let me just point out what happens to this formula here. This say left reduction, and then this has sort of counterparts everywhere. What we did, right? We wrote down the Taylor series of A. So we had things like z minus z prime to the alpha, and then d z prime alpha of A. So this is unchanged. I mean, just because I put an H there, that doesn't change the Taylor series of A. So this was at z, z, zeta. So, but now, this z minus z prime to the alpha of the exponential. So beforehand, I had a minus d zeta to the alpha of this exponential. But now if I do this differentiation, I also get a power of H down. So altogether, now I have an H to the alpha. So the upshot is that in the formula, we get a sum over alpha, I to the alpha, alpha factorial, and then you also get an H to the alpha now, and then whatever it was before, dz, maybe it was the way I wrote it, it's a straight d. So the upshot is that we actually, so H here, remember, is possibly going to 0. And I'm certainly bounded, so it doesn't make anything worse. But possibly it's going to 0. And in fact, going to 0 is the interesting case. So the point is, as H goes to 0, we not only gain in terms of decay in the z and zeta variables, but we also gain in H. We also gain decay in H. So there are, so correspondingly, what you really should do, maybe I will do it before the break now, is to really correspondingly also get the symbol. We get the semi-classical symbol at H equals 0. Okay, so the upshot of this will be that this pseudodifferential machinery, for example, when you have an elliptic operator, it allows you to construct an approximate inverse, a parametrics for it. And so what does this mean? Well, in a compact manifold, this would be constructing an inverse modulo of finite dimensional error. But there is this finite dimensional potential error, which has to be there because, take a Laplacian on a compact manifold, it's going to have eigenvalues. So Laplacian minus an eigenvalue is not going to be invertible. So it has to be there. But in this semi-classical sense, what you can arrange is that your errors actually small. They are order h to any power, h to the infinity, if you want. And so at the end of the day, what happens when you construct an approximate inverse? Well, it's approximate, so that's identity plus an error. And this error could be, I don't know, smoothing operator, the C infinity Schwartz kernel. That's not guaranteed to be invertible, even if it's identity plus compact, for instance, right? On the other hand, identity plus small is guaranteed to be invertible. So in this semi-classical picture, at least for H sufficiently small, we automatically get invertibility results. So it's not just approximate invertibility. So this is actually very useful. So let me just reinterpret this principal symbol, and then we have a break. And then the second half, we're going to do we're going to use all this. So the way I want to reinterpret is the following. So I mean, I said here you take quotient spaces and whatnot. So that's not so obvious what this means geometrically. So if you talk about this classical symbol, so let me just do the sub-infinitive first of all. So if you talk about this symbol class, but so let's do the classical version. So this just means you have expansions. So when you have something like this, so A is in here. So that means A looks like, so I'm just going to, Rn Z. Rn zeta, so I can get rid of the zeta prime variables. So this means that A has an expansion, right, sum, and then it's going to be, you can write it like this, zeta, so this is an expansion as zeta goes to infinity. So, I mean, it's not a problem that the origin is of course, singular if I put down something like m minus j here. And then at zeta hat, so zeta hat is just zeta over magnitude zeta. So it has an expansion like this. And so here you can take, one can take the A0 term, so A0 as the representative, as the canonical representative of this equivalence class. So what we are doing here, this is a homogeneous, I can't remember, maybe in my notes I use a different notation, but anyway, that's what I have right now. This is a homogeneous degree m function in zeta. I mean, so this is, the homogeneity is in zeta. So that is to say, in the dilations in the zeta variable, you have this homogeneity. Okay, so now it's a bit more concrete. We have a concrete representative. But what's even better is if we do the following. So I'm going to do this for m equals 0. In general m, you can either say that you can put in some extra structures like line bundles, or that it doesn't matter anyway because the things you care about make sense, even if the total object does not. So if m equals 0, so in this case, remember that this says exactly that A is a smooth function of, well, let me just write it this because I didn't really discuss the behavior in this case at infinity in Z. So I'm not leaving this compact, but I'm making this compact. So this is Z, and this is zeta. So zeroth order, and having an expansion is exactly the Taylor series at zeta equals infinity. And so then the picture I want to draw, so here's my non-compact Rn, but now I have these, this ball bundle, Rn bar over it. And so this whole thing is really, the way you should think about this is, so you should think about this really that you're taking the cotangent bundle of Rn, that will be without the bar, and then you're compactifying the fibers. So the fiber compactified. So that's what is really going on here. So this is an Rn bar, but what really happens here, the place where we see this principal symbol, so the A0 term, is really at the boundary of this Rn bar. So the Rn bar is a ball. So this whole thing is a ball. But then here at sort of infinity at the boundary is a sphere. And so you can the way you can think of A0 is just the restriction of A to the boundary of Rn cross Rn bar, i.e. to Rn cross the n minus 1 sphere. So, I mean, let me get rid of the roundification. So here's my z variable. Here's my zeta compactified variable. And what we are doing is really just restricting to here. So A0 lives here. Right? If I instead had an order m operator, then the only problem is that I have a zeta to the m floating around. So I can renormalize if I have decided a fixed choice of zeta to arrange this. If I didn't decide this, then I have ambiguity. But in fact, anything that you care about will not depend on this ambiguity. So you would have to check that. So let me just say that let me just draw the analogous picture for the ML world, just to illustrate the difference. Okay, here's the ML. The ML picture. So if I now take, again, an A, which I'm going to make 0, 0 classical. So this is to say, now if and only if it's C infinity on the product of the compactifications in the two variables. So if I do this, then here's my analogous picture. This is my Rm bar in Z. This is my Rm bar in zeta. This is the fiber variable. And then what I can think of is that this class of A, actually, this can be identified with the restriction of A, again, to the boundary of this product. But now this has two boundary hypersurfaces. I mean, this is a manifold with corners now, so it has two boundary hypersurfaces. There's fiber infinity, which would be Rn bar. So the base is still compact, but across the boundary of Rn bar, so the sphere. And then there's sort of a base infinity, which is now a boundary of Rn bar across Rn bar. And of course, it's intersect at the corner. And so, when we talk about principal symbols, at least for this somewhat slightly restricted class, and so in general, this also gives you a good intuition. And sort of have to, I don't know, sheafify it or something to think about it more generally. You really think of these. You can really think of these objects as functions. These principal symbols as functions on. Well, it's not quite a manifold in this case. Here it's a manifold. Here it's manifolds with boundary glued at the corner. So with an identification at the corner. And in fact, the semi-classical picture would be completely similar. If I really want to do, I could do, for example, this with the semi-classical parameter added. So then I would have an h that's coming out of the board. And then maybe the board would be h equals 0. And so what would be happening is that I would have then a product of these two things as well as an interval. And at h equals 0, it should be at the board, I get the semi-classical symbol. And then on these other sides, so even for h positive, on the other side, I get this sort of more standard principal symbol, which I all combine together. So then I get a much more, an even more complicated looking picture. But it's all really, it's really just, it's nothing messy really here. We're just talking about manifolds with maybe corners and specifying something on the boundary hypersurface of it. OK, so let's take a break. All right, so let's continue. So maybe I erase. Actually, maybe I keep this for a moment. I want to have one more object associated to a pseudodifferential operator. So far, we have pseudodifferential operators, and associated with them, we have a principal symbol, which we defined it as an element of some quotient space. But in these nice cases, we could really think of these as functions on some manifold. I also want to, and so what the principal symbol measures, let me maybe make a definition. So an operator is elliptic. So say A in psi ml is elliptic if its principal symbol is invertible. In the sense of these quotient spaces, so you can say this in various senses. So notice that in the classical case, this just amounts to this function we get on the boundary of this compact space, just amounts to this being non-zero. So I haven't said anything about matrices of operators, but of course you could have matrices of operators, and everything works similarly. Of course, composition is not commutative now to leading order even, but that's only because of matrix multiplication is not commutative. And so then what you would have is this, if you have the matrix of operators, you would get the matrix of symbols, and then the non-zero would just is invertible as a matrix. So there's nothing surprising there. And the analogous thing here, sub-infinity, is elliptic. So again, in here, if A, which is just sigma m, sigma infinity m of A is invertible. So, what we are imposing in these two cases is something quite different as far as ellipticity is concerned. In the second case, in the sub-infinity case, we are just imposing something at fiber infinity, while in the other case, we are imposing something at every boundary phase. Yes? Right. So I really mean this is invertible in the sense of this symbol class. So there's so maybe to be more careful, i.e. Exists some b in the opposite in minus m infinity, such that ab is so ab is 1 mod I could say s minus infinity or even s minus 1, doesn't matter. Let's say s minus infinity. That would be. but so here we are really requiring something just at fiber infinity, while here we require something both at fiber infinity and base infinity. And so correspondingly, we get an elliptic set. So this is elliptic period. You can also say that A is elliptic at a point. Sorry. So say in the first case, is elliptic at the point, say alpha in this boundary. If it's lila a, which is again the same thing, is invertible in a neighborhood of alpha in Rn bar cross Rn bar. So again, this classical setting is just the statement that it's non-zero. So in classical setting, it's just the same. It's not equal to. well, I mean, classical zeroth order. Otherwise, you have to do a renormalization, right? You have to put in some homogeneous function to get it the right homogeneity. But again, being non-zero is a property that's independent of multiplying by positive functions. So even if I have an arbitrary order ML here, whether something vanishes or not, if that something is defined by multiplying by positive factors, is actually well defined, even if the thing itself is not well defined. All right, so correspondingly, I get the elliptic set of A. This is the elliptic set. So this is going to be a subset of this boundary. And I get the characteristic set, which is the complement. Well, within the boundary, that is. OK, so okay, as I said, I want one more notion that's related to these pictures. So maybe I erase this one. Which is the operator wavefront set. So again, if I write A as the left quantization of some little a, so we are in a picture like this. I want to have so I didn't say this. So I meant to say, but I didn't say this. So what the principal symbol measures, so ellipticity in particular measures, so non-zeroness of the principal symbol measures, is something like the operator being non-degenerate. So ellipticity is so it's a non-zero property, it's an invertibility property, somehow non-degeneracy property. So that's very good to have a non-degeneracy property. The other thing you might want to have is a complete degeneracy, like triviality. So this measures, in other words, principal symbol sort of measures or captures, in some ways, non-degeneracy. And under the wavefront set, what it will do is this measures complete triviality. So, right, so we have this, these operators, this psi ml, they get better when the order gets more and more negative, the order minus infinity being completely trivial. And we would like to say that even if you have a random psi dio, we would like to be able to say that, well, this operator might not be order minus infinity. It might be non-trivial globally, but at the places that we care about, and maybe say I have my alpha here, that at this alpha, it is actually order minus infinity. So there are some options of exactly what you do. So I'm just going to do the following, but you could have other options. So the definition is that a point alpha in the boundary of this compact space is not in the operator wavefront set of A if, again, alpha has a neighborhood in Rm bar cross Rm bar such that A on this neighborhood is order minus infinity. So it's trivial. Okay, so here I use the left quantization, just like I used. So for the principal symbol, I already said it doesn't matter whether you use left or right. It's the same thing because of the reduction formula. On the other hand, certainly it makes a difference for an operator whether you use left quantization or right quantization. But for this property of being trivial, it doesn't make any difference. So note that is equivalent this is equivalent to if you write A as the right quantization, say, of something. So there are other choices too, but let's say we use this, that AR is trivial near alpha. And so the reason for this is just look at the reduction formula. Right, the reduction formula, this left reduction formula, so we simply have to rewrite this to check the definition. It only has derivatives, and derivatives are local, so no problem. Okay, so now we have we have two notions. We have this notion of a principal system, but we have this notion of a wavefront set. Now, so also directly from the definition, let me say that, well, directly from the definition, the complement of the wavefront set is open, so the wavefront set itself is closed. Directly from the definition. So the complement is really open. Okay, so this notion of triviality, so where the operator is trivial, is an open condition. Non-triviality is the closed condition. Okay, so so this explains. Maybe I should say one property of this before saying the explains. So notice that if you have two operators, so have them whatever orders, well then the product is going to be trivial where one of these two factors is trivial. So in other words, the wavefront set of AB is sitting inside the wavefront set of both. This is just because if either, if you write this quantization, either little a or little b is trivial near a point, so are all the derivatives. And so hence by the composition formula, hence the product of the two. And so by the composition formula, conclusion follows. Okay? Yes? Right. Right, it's just so that I don't have to say things separately. So of course, if you're at a point, if I have an alpha here, then the second order is irrelevant. And if I have an alpha here, then the first order is irrelevant. And if I'm at the corner, then they're both relevant.
It's irrelevant because you are not at infinity.
That's right. That's right. Exactly. Yeah. So this is just to uniformize things, to make it things. That's right, you get both. So usually it's only going to be one of the two things that's relevant, but at the corner both are relevant. Yes. Thank you for asking this. Okay. All right. So we have now the basic sort of algebraic properties here. We would like to use this. So let me point out some uses. So one is starting with ellipticity. So, the first maybe proposition is that if you have an elliptic operator, then it has an approximate inverse. Are trivial. Okay, versus if I have this statement, sub-infinity. So if I have ellipticity in this algebra in which you gain both in derivatives and in decay, so both in zeta and in z, then you can invert elliptic operators modulo operators are trivial in both senses, while in the sub-infinity case you can invert them modulo operators that are trivial in the zeta sense. And so I'm not going to write in a full proof, but I'm going to give the idea because it's very easy. So the idea is simply that let's start. So first guess. Let's just use the principal symbol. So certainly if we have such A and B, we must have that the principal symbol of B as an operator of this order has to be, multiplied by the principal symbol of A has to be that of the identity. So it has to be 1 over the principal. So I should say the principal symbol of the identity is 1. Right? It's a differential operator, so it's easy to write down. It is. It has to be equal to this. Again, in a principal symbol sense. So somehow this is really in a quotient space, i.e., somewhere near the boundary of this compact space. If you're in a classical sense, then it's honestly just on the boundary, period. So we must have this. So what we do is just take any. So ellipticity, by the way, means that this is OK, division by A because of ellipticity. And if you had this system, a matrix, then you just want to invert the matrix. So take any B, 0 for starters, with principal symbol 1 over sigma MLA. And so if you do that, so then what you get, then if you take B0A minus the identity, so this is going to be a priori an operator. So this is operator order 0, 0. This is an operator ML times minus M minus L. So it's a priori an operator of order 0, 0, but with principal symbol. Principal symbol of A divided by itself, minus 1, so 0. So what I said, the short exact sequence statement basically says that therefore B0A minus identity is equal to E, which is an operator of order minus 1, minus 1. 1 order lower in both senses. And now what you get, so i.e. B0A is I plus E. And then now what you do is you just want to invert this INT plus C. Well, you can't quite invert it, but you can sort of invert it by using Neumann series. So just write so if you just take a finite sum, maybe m minus 1, e to the j, you take something like this, and then multiply it by, I want to multiply it on the right. So it's just INT, whatever power I get. I don't know. So I don't know whether I get my signs right, but let's hope I do. Anyway, it's something like this times e to the n. And so the point is that this is in psi minus n minus n. So now I can just multiply by this from the left. And so therefore, if I write Bn A is equal to INT plus En, if Bn is just Ej, e to the j, sorry. And the point is that this thing now is in psi minus n minus n. So this is not quite what I wanted. I wanted minus infinity minus infinity. Again, A, it never matters. You could live with this for any practical purpose. And if you want to be a perfectionist, what you do is just do an asymptotic summation argument. to get complete conclusion. But again, it's really irrelevant for almost any application. Okay, but yes? A B note, yes, thank you. Thank you. All right, so the upshot is that now we have approximate inverses at least for, so I got the left inverse, which was the left inverse I got. I got the left inverse, that's almost approximate left inverse. I could similarly get an approximate right inverse, and then use, so the parametric identity, which is basically the resolvent identity when you don't quite have a resolvent, to show that the two are same up to a trivial term, which by trivial mean again the same thing. So that's that sort of proves the lemma, the proposition, and then the same argument works, but you only gain in one sense to prove the other half. Okay, so that does ellipticity. Now, okay, so I was going to say something that I can't quite say yet, so I better do something that lets me say that. So that was one use of this algebraic machinery. Another use is L2 boundedness. So, of course, not all pseudo-Us are L2 bounded, like differential operators have a tendency of not being so. But so if you take an operator of order 0, infinity, so in particular, I mean, the operators 0, 0 sit inside here, so this is fine. So this implies that A is actually a bounded operator on L2. Okay, and so I mean, you can do this in various ways. So this had been done, of course, a long time ago. I mean, a very long time. But then Hermander has a particularly neat proof. So here, Hermander's proof relies on a approximate square root construction. So maybe I shouldn't call the operator I'm square rooting A. I think I can't think of a good. Let's call it T. So if you have an operator T with the which is order 0 for the actual application, so you have an operator of order 0, and let's assume that its principal symbol is actually bounded below by some positive constant. So you have a uniform bound for this. Then the statement is that then there exists some operator G, let's call it B. There's a B, again, of order 0, infinity, such that so let me actually also, just to make my life easier, let's make T equals T star, so that I can say the final thing I want. So it's just the formal adjoint, such that T is equal to, so first of all, B is equal to B star, and T is equal to B squared, or it should B star B, modulo trivial error, plus E, where E is in psi minus infinity sub infinity. So it's smoothing in this sense. Okay? And so to construct this, basically all you do is essentially you take the square root of the principal symbol of T as your initial guess for B, and then sort of similarly do a sort of similar construction. So really just iterate to, I mean, there I just wrote down the Neumann series, but even if you didn't know how to invert something identity plus E by just writing down the Neumann series, you could just, okay, I want to have a series with terms of various orders and iteratively find them. So in this case, maybe you don't know from the top of your head how to invert it, but you just calculate it and you find it. So the idea is you just take B with principal symbol square root of t, where t is the principal symbol of big T, and iterate it away. OK, so once you have this, you're in a great shape. And again, really, minus infinity doesn't matter. Sufficient negative order is what matters. So the point is that if you have an operator E, which is of sufficient negative order, so directly depends on how much work you want to do. If E is psi minus n infinity and sufficiently large, then it's very easy to see. I mean, it's super easy without any work. So in fact, n strictly positive is not hard, but n bigger than little n is really easy. Very easy. Then certainly E is L2 bounded. I mean, I should say that, again, this is not really a statement that, this is not really the only statement you want to have. You really want to have a statement that ends the map from psi DOs. So you can think of psi DOs as topologized by symbols, right? Because of the, say, by the left quantization map. So you really want to say that the map from symbols of psi DOs to operators is a continuous map. OK, so this is very easy because this is really Schur's lemma. Right, so basically, this is the L infinity L1 bounds on the kernel in both ways. So in this case, you very easily see that the Schwarz kernel is continuous because the integral actually converges. OK, so actually it converges, and in fact, this is something I didn't say, but I should have said. The Schwarz kernel in general of a psi DO in general is C infinity. So it's, again, the same sort of integration by parts argument. It's C infinity away from the diagonal. This is basically coming from the fact that we use this z minus z prime for this zeta integration by parts. That basically, that's what you need to be able to just divide by that, hence the diagonal, and rapidly decreases. I mean, with all derivatives. So it's really short as z minus z prime goes to infinity. This is in general the case, but if you have an order which is sufficiently negative, then in fact the Schwarz kernel is continuous at the diagonal, and so you get everything that you want very cheaply. All right, so operators of sufficient negative order are easily seen to be L2 bounded, and then to deal with operators of order 0, what you do is now if A is in psi 0 infinity, what you're going to take is well, let's think about first A star A. And then what you're going to do is you're going to take a constant and let C be such that C is bigger than the sup of the principal symbol of A squared. Doesn't matter. So if I do this, so that's the sup. I mean, A squared is the principal symbol of A star A, right? So that's why I wrote it down. Right, this is A bar A. So if you do this, then C minus A star A is satisfies the assumptions. And so what you get is that C minus A star A is equal to some B star B plus some E, where this E is trivial in some sense. And so what this tells you, that for Schwarz functions, if you apply this to a Schwarz function phi and pair it with phi, what you get is C times phi squared minus maybe E phi phi. But by the L2 boundedness of of E, this is going to be bounded by some other constant times norm phi squared. This is greater than or equal to the sum of two things, both of which are non-negative, a phi squared. So this is equal to, I guess, the way I write it. They're both non-negative, so in particular, it's greater than or equal to the norm of a phi squared. And so again, this is just some constant. This is bounded by some constant times phi squared. So this tells that up to this trivial term, which again is bounded by some constant times phi squared, a bound for a phi is given by this c, which is really the supremum of a squared. Okay. So that shows you that for Schwartz functions you have this bound, and then so automatically you have a unique extension to L2. Okay, so that's the L2 bound. So I didn't say actually another thing, which is that one use for proving that the adjoints of pseudodifferential operators is the fact that pseudodifferential operators not only act on Schwartz functions, but they also act on the dual spaces. So that's just the usual dualization argument. So they act on temporal distributions. Okay, but so now we have that they do all the good things. They all act on Schwartz functions. They all act on temporal distributions. And operators of order 0 act on L2. Okay, and so we of course do want to have Sobolev spaces as well. And so the Sobolev version so Sobolev spaces. So if I think I already defined this. So if we take Sobolev spaces H as R of Rn, so this was z to the minus R times Hs. Of Rn. And so what this is really is, right, z to the minus R. I can write as the inverse Fourier transform of multiplication by zeta to the minus s times the Fourier transform of L2. That's just what the Fourier transform is. I didn't mess up my signs. And so this thing here is a pseudodifferential operator of order minus s, comma minus r. And it's certainly, it's not, of course, you can actually invert this, where the inverse would just have the inverse of this on the other side and have the inverse of this in the middle. And so what this tells you is that the L2 boundedness of 0 Thodep psi dios. So if I use this, then it's really 0, 0 Thodep psi dios. Psi dios plus the algebra properties of psi dios imply that if A is a psi dio of some order, so if A is here, then A is a continuous linear map from H SR to H S minus M R minus L. Oops, sorry, I don't need an arrow here. I need a comma. So this sort of pops out immediately, because essentially what this means, if you rephrase this boundedness statement, that's really a boundedness statement of some operator from L2 to L2, and the operator is sort of a conjugate, not quite conjugate of A by these sort of psi dios. So the algebra property implies that. Okay, so we have Sobolev spaces as well. These things act on Sobolev spaces. So a consequence well, one direct consequence is elliptic regularity. The consequence is elliptic estimate. So maybe I'm just going to say the global version, and I'm going to I want to say the microlocal version. If I get through to that, then well, I'm not too much behind, but I'm still behind, of course. So the elliptic regularity statement is just that if A is elliptic, and AU is in a Sobolev space HS minus M. So elliptic and U a tempered distribution. Right, so tempered distributions are just the union of all the weighted Sobolev spaces. So if AU is in here, this implies that U is in HS R. So the proof is really easy. The proof is just take B be an approximate inverse, so be a parametrics. Maybe I didn't use this, so let me say it. This is approximate inverse in the sense before for A. And then use that U. So this says in particular that BA is equal to identity plus E, where E is order minus infinity in every possible sense. And then BA, so U, is equal to BAU minus EU. And so we are assuming that AU is nice. So it's in this space. And then B, so the parametrics has the opposite orders to A. The negatives the orders of A. So this, by our Sobolev mapping property, this is going to back up to, this is sitting in HSR. On the other hand, this E is a smoothing operator. So remember this, as I said, this is the union of all the weighted Sobolev spaces. So in particular, U is in one of these spaces, whichever one it is. And then, but then E has this minus infinity here. So this is the general statement that infinite goodness always overcomes finite badness. So so this is a union. So this means things are finitely bad. But here's the infinite goodness. So so this thing here, on the other hand, is actually, this is in fact a Schwartz function. So that's the intersection on the other hand. So so this is infinitely good. So this whole thing is in HSR. OK, so this was very easy. Now, if you want an estimate version, it also provides an estimate. Namely, I mean, I should say that at the end of the day, you can always recover estimates by the closed graph theorem. But it's sort of a very roundabout way of recovering estimates when you get them directly. So the estimate you get directly from this formula is that you can estimate U by a constant times. So that just comes from B. So U in HSR is going to be bounded by a constant times AU in S minus M R minus L plus some norm. And doesn't matter what it is. So let me call it big M comma big N. You have an estimate like this for any Mn. Meaning C, of course, will depend on Mn. You don't think of really varying Mn. Mn is going to be your favorite very negative numbers. Okay, and then there's a C such that this estimate holds. So this is the basic elliptic estimate. So then this is really the Fredholm estimate that we needed. So remember before, this is really a Fredholm estimate. Also, notice that if A is elliptic, then its adjoint A star has principal symbol A bar, so it's also elliptic. Okay, so A elliptic implies A star elliptic, because principal symbol is A bar. And so we have a similar estimate for for A star. Okay, and so the two put together, you really care about which estimate you really care about. Actually, the estimate you really care about, so let me write it maybe down once. You have an estimate like phi, and then I want the dual space of this. So that's really minus S plus M minus L plus R. This is going to be less than some constant times A star phi. And I want the dual space of that, so it will be H minus S minus S minus R. Sorry, I messed this up. Right, I was trying to take the negative of this, so it's minus R plus L. And so this is exactly right. So this is this plus M. This is this plus L. So plus, who knows what. This doesn't really matter. Some space, you get an estimate like this. This is exactly the dual spaces. So the general abstract Fredholm theory is applicable, which implies that that A as a map from H SR to H S minus M R minus L is actually Fredholm. So closed range, fine dimensional kernel, fine dimensional co-kernel. So this doesn't quite give, of course, invertibility. This is invertibility up to a fine dimensional obstacle. Up to. And so that doesn't even mean invertibility up to possibly perturbing it by something compact, because the thing that you will be looking at is the index of this operator. If the index is 0, that Fredholm index is 0, that's exactly the statement that you can perturb it by, even a psi d of order minus infinity to make it invertible. Anyway, it's in general Fredholm, which was what we really wanted. This is the sort of framework that we wanted to get at. Now, if you're in a semi-classical version, so if you have an A that's elliptic even semi-classically, so I mean, remember, so there's an extra symbol, semi-classical symbol. I didn't quite write it down. Is that is that H equals 0? Then what happens if you go through this argument? Then in fact you get an E. So when we get the parametrics construction gives that you get a B, such that B A minus the identity is equal to E, which is, let me write it this way, it's in H to the infinity. So it's trivial in the H sense. I just don't want to have too many indices on the psi. So I'm just going to keep the usual indices here. So it's trivial also in the semi-classical sense. And so this in particular implies small, as I indicated at the end of first half of the lecture. Small in L2, say, in particular when H is small. And so therefore, identity plus E is invertible. Yes, that's what I want. For H small, and then and so the upshot is that you're honest in an invertible situation. So this is I talk more about semi-classical things tomorrow, but I just want, I mean, this sort of fits exactly into the, I didn't want to postpone this since it's sort of very natural here. All right, any questions? No? Okay, so what I want to do in the last 50 minutes is or not quite 50 minutes, is to say that there's a microlocal version of this, and then maybe just say a few words about what we're going to do next time. So the microlocal version, so I talked about what it means to be elliptic at a point. So I also want to have a similar statement. I mean, this elliptic theory doesn't do justice to microlocal analysis in that basically no matter what you do, elliptic problems are well behaved. They're so good. A reason why you want to be in phase space, or why you want to do microlocal analysis, is, for example, to look at things like wave propagation, where things really are happening in phase space. I mean, as for example, this Kerr example, how the geodesics behave. I mean, they look, when you project to the physical space, they look horrible, right? For example, the photon sphere got distorted, but when you're upstairs in phase space, nothing really happened. So you really want to be in phase space. So elliptic theory doesn't do justice to that, but we get to the non-elliptic things next time. So the the microlocal version is if you have an operator A is elliptic. So let's start first the parametrics part. If A is elliptic at a point at some alpha, well, then there's a microlocal parametrics for it. So I didn't give it an order. Then exists B minus L such that, well, so let me give these names. Sorry, AB. So, well, these things are just imply 0, so that doesn't sound very good, right? If I take any B of this order, this AB and BA are already imply 0, 0, and the identity is there, so this differential is imply 0, 0, so it doesn't sound very good. But, so this is true, and the wavefront set of EL and the wavefront set of ER are disjoint. Well, alpha is not in them, the way I wrote it. So i.e. EL and ER are trivial at alpha. So more generally, I could do this. Same works with alpha replaced by a compact set. Okay, and so basically what you do is really do the same argument, except that, so remember what was the parametrics construction argument? The parametrics construction was that you first took the reciprocal of the symbol of A, and then you used this Neumann series to, so that gave an error, which was one order better than you a priori had, and then you use the Neumann series to sum it. So now, so the proof is that, that the locally, so near alpha, the symbolic construction of the parametrics works. Okay, so I mean, there's just one slight thing to say that you're really, the way I wrote it down, I really wrote down honest compositions of psi DOs. I had this e to the power j, but again, I really cared about this modulo order minus infinity operators, and the composition is symbolic, so it doesn't really matter. All right, so we have the same construction, and then the upshot, if you just run through these arguments, is the following. So it's really exactly the same argument. We get microlocal elliptic regularity and corresponding estimate. So what does this say? This says that so if A is elliptic at alpha, let me say it imprecisely slightly, and then I'm going to say something more precisely. And AU So I'm going to give a more precise definition of this in a second. And AU is in H S minus M R minus L. So this was psi ML. Microlocally at alpha. So then U is actually in HSR microlocally at alpha. So what does this microlocally at alpha mean? So what this means is the following. So again, we really think of this picture. I had this compactified phase space pictures, right? So this was R and bar, and then this was another R and bar, and the whole thing is just a product. So one way to put things is that we can really think of, say, classical pseudodifferential operators of order 0 as a quantum version, a quantized version of a partition of unity. So, so psi DOs of order 0, 0 can be thought of as like bump functions, are sort of cut-up functions. Well, quantized, that is. Quantized, and if you put them together, you can do like quantum partitions of unity. So they're cut-off functions. So one way to say this is so U is in HSR microlocally at alpha means that if there exists, let's call it I don't know G in psi 0, 0. In fact, let me just make it. It's pretty much irrelevant what I say here, but let me just make it classical because then we have a very clear picture of what's going on, like this elliptic. So that just means its principal symbol is non-zero at alpha, such that GU is in HSR, honestly, globally. Okay, so another notation for it, one also says that that alpha is not in the SR wavefront set of U. Okay, so so you think of this G. So I don't know. Maybe this the principal symbol little g of this big G could be something like this, some bump function. This is my alpha. So this is the principal symbol. Sorry, 0, 0. Of big G. So it's some bump function. It's non-zero at alpha. You think of this as a sort of a cutoff. So you say that the function is microlocally nice at alpha if there's such a quantized cutoff. G, such that GU is in the space that you want. Okay? And then, of course, this way, I mean, it's a there exists statement, so it doesn't, I mean, okay, but, you know, could I take a different G? So then it's basically, again, exactly this microlocal parametrics construction, so this G was elliptic at alpha, says that, in fact, the choice of G is irrelevant. It's not just that there exists, it's really a for all G with sufficiently small wavefront set that this holds. So, so this there exists is really a for all with an extra qualifier. Okay, and so then with this microlocal elliptic regularity follows automatically from the by the same proof, just sort of writing everything out. And then another consequence is the estimate. So let me just write down the estimate. Maybe I shouldn't erase some of these things. Okay, so the microlocal estimate then would be something like this. It's going to look very similar to what I had, but I have to put in a microlocalizer. So let's call it B1. Something like this is going to be bounded by a constant times, let's call it B3 for a change. H S minus M R minus L plus some, who cares what, very weak norm of u. And so what are these b's? So this b1 and b3 are, I wrote this because I'm going to talk about propagation of singularities next, and for that I'm going to have a b2 as well. So this way the notation is the same. So these are operators of order 0, and what we need is that the wavefront the wavefront set of b1. So where b1 is non-trivial has to be where b3 is controlling it. So sitting inside the elliptic set of b3. And A is elliptic on the wavefront set of B3. So the picture is that, so maybe I do another one like this. So I have this, I have the elliptic set of A, so that's an open set. So this is something like the elliptic set of A. And then I care about what happens at some point, or maybe on some subset. So I'm going to have some B1. So something like this is going to be the elliptic set of B1. And then maybe the closure of that, roughly, is the wavefront set. And then if I choose sort of a B3 that's intermediate, something like this, B3, then I can control what happens microlocally at sort of where B1 is non-trivial in terms of what happens on a sort of slightly bigger set. So notice that there's a slight increase here, right? The wavefront set, so this says where B1 is not completely trivial, has to be inside where B3 is actually elliptic. So it's a very non-degenerate. Yes? I could, but so I just want to leave. So you're given an operator A. I said that, well, if it's only elliptic somewhere, I can just put in a B3. So, yes, I could. Yes. OK. So so that's the basic microlocal elliptic estimate. Now, what I'm going to do next time is to go sort of beyond ellipticity, and so. What we will do is do positive commutator proofs. So we're going to do two things via positive commutator proofs. So you should think of these as microlocal energy estimates. So if you think like energy estimates for wave propagation, this is what this is analogous to, but sort of done at the phase space level. And so what these do is the sort of things that we're going to have an operator P, which is not going to be elliptic, but has real principal symbol, lila P, and then we'll have which has a non-degenerate 0. 0, so I mean dp is non-zero where p vanishes. So then the characteristic set is now smooth codimension 1. Codimension 1. And so once you have this, you can talk about the Hamilton vector field HP. So this is what corresponds to the Poisson bracket, right? So HP is sort of defined by this relation, and then I wrote this down before. And so HP is the Hamilton vector field. And then Hermander's theorem on propagation of singularities is that you can propagate Sobolev estimates. Well, this is, I guess, not quite Hermander's theorem if I put it this way. But anyway, HSR estimate, Hermander plus, HSR estimates propagate along HP integral curves, which are called bicharacteristics. And so just to have the analog of the statement there, so the upshot will be a statement like this. You get estimates like this. You control U somewhere by controlling U somewhere else. Right, this is the propagation plus controlling PU somewhere, controlling PU in between. And then in this process, you lose one derivative relative to elliptic estimates, plus some trivial term that you don't care about. So some estimate like this, where the picture is the following. So let me just draw the picture and then stop. So in order to have a somewhat interesting picture, my board is just going to be Rn across, say, the boundary of Rn. So I'm just drawing a convectified. So this is my board. So I'm just drawing a local picture. And in fact, I'm just going to drawing the characteristic set within it. So here are the integral curves. This is the HP integral curves. And so the what will happen is that I'm going to have something like this. This is going to be the wavefront set or elliptic set, whatever, of B1. And I want to control U here. And I can do that provided I control, this is going to be the, say, elliptic set of B2, provided I control U over there, and provided I control, so this thing is going to be the elliptic set of B3, and provided that I control PU in between. Okay, so you propagate, you can propagate estimates from somewhere to somewhere else, provided that you control PU in between. So this is exactly like wave propagation. Think of this as like a thickened version of a Cauchy hypersurface, except that you are in phase space. This is where you want to get control. So maybe it's a future time slice. So of course you also of course get the estimate everywhere in between. So maybe a bare picture would have been like that. And so you control, in terms of initial data, you control what happens later on, provided you also know that you have a solution of the wave equation or in whatever sense. All right, so thank you. Any questions? Okay, thank you.